Hello students, welcome to the lecture number 9, Basic Electrical Engineering, Jntuh previous year bit paper questions and solutions. These are the first mid previous year questions and solutions, unit number 2 AC circuits. In this lecture, we will discuss RL, RC, RLC series and parallel circuits. Fill in the blanks previous year questions and solutions. Let us start with the first question. Question number 1. The length of a phasor in a phasor diagram normally represents dash value of the alternating quantity. In the phasor diagram, phasor is representing what kind of AC value. So phasor diagram, phasor value is going to represent RMS value. It represents the RMS value. Question number 2. The current through the inductor is dash with respect to the applied voltage. In the inductor, in the inductor does not allow sudden changes in the current. So in inductor, current is lagging behind the voltage. So with respect to the applied voltage, the current is going to lag. So lags behind. Current lags behind the applied voltage, or current lags with respect to the applied voltage. Question number 3. The phase angle between voltage and current in a pure inductance is. In case of pure inductor, current lags behind the voltage by 90 degrees. The phase difference between voltage and current in pure inductor is, phase angle is how much? 90 degrees. Question number 4. In pure capacitive circuit, the current will be. We know capacitor does not allow sudden changes in the voltage. Therefore, voltage will be lagging and current will be leading. In pure capacitive circuit, the current will be leading the applied voltage. Current will be leading applied voltage or voltage across capacitor. Next, question number 5. The power consumed in pure inductive circuit. So the power consumed in the pure inductive circuit is going to be 0. Next, question number 6. The capacitive reactance of a circuit dash with the increase if frequency. So capacitive reactance, what is the formula? Formula of the capacitive reactance Xc is equal to 1 by 2 pi Fc. So if the frequency increases, what is going to happen with the capacitive reactance? Let us analyze. As the frequency increases, this denominator value is going to increase. 2 pi Fc value is going to increase. So this means 1 by 2 pi Fc value is going to decrease. So increase in the frequency causes capacitive reactance Xc is going to decrease. So the capacitive reactance of a circuit decreases with the increase in the frequency. Question number 7. In an inductive circuit, when the frequency of the applied voltage is increased, so frequency is we are increasing, then what happens to the current? So in inductive circuit, current I is equal to V divided by inductive reactance XL. So that is equal to V divided by XL is nothing but what? Inductive reactance is 2 pi FL. So what it is asked here? Frequency is increasing. So F value is going to increase. F value increases means 2 pi FL value is going to increase. This means V by 2 pi FL value is going to decrease. So this V by 2 pi FL is nothing but what? Current. So current value is going to decrease. As the frequency increases, current in the inductor is going to decrease. So current will decrease. Question number 8. If the supply frequency of purely inductive circuit is doubled, so let us say F1 is equal to F, but frequency is doubled. Doubled is nothing but what? 2F. The circuit current will become what? So let us say initially I1 is equal to I, and what is the I2 value we need to find out. In both the cases, applied voltage V1 is equal to V and V2 is also equal to V. So what is the usually I1 formula? I1 is equal to I is equal to V divided by XL, that is equal to V divided by 2 pi F1L, that is equal to V divided by 2 pi FL. Let us say this equation number 1. And I2, after the frequency is doubled, we have to calculate the I2L, V divided by XL. This is XL1, let us say it is XL2. V by 2 pi F2L, that is equal to V divided by 2 pi F2, sorry, 2 pi F2 value is how much? 2L. So this I am writing as, just you see, V by this 2 pi FL is there, that I am bringing outside, 2 pi FL into this 2 is there, 2 I am keeping outside. So V by 2 pi FL is nothing but what? I1. So I1 divided by 2. I2 is equal to this value. You see, this value is I1 into 1 by 2. So I1 by 2. So current is becoming what? Half. When the frequency is doubled, current is becoming half. That means current will be halved. Question number 9. The capacitance of dash will give the same reactance as the inductor of 1 Henry at 50 cycles per second. So we know inductor reactance is equal to XL. So how much inductive reactance is there? In order to get same amount of reactance, what is the value of the capacitor? We need to find out. So XL is equal to, what is the formula? XL is equal to, what is the formula? XL is equal to 2 pi FL. So and XC is equal to 1 by 2 pi FC. So both the reactances must be same. So then what I am doing here is XL and XC both I am making equal. So XL is equal to 2 pi FL. 2 pi F into L is equal to 1 by 2 pi F into C. So here what is given, inductance value is 1 Henry. So L is equal to 1 Henry, and 50 cycles per second is nothing but what? Frequency is nothing but what? 50 cycles per second. 50 cycles per second is 50 Hertz. So what value we need to calculate? Capacitance C value we need to calculate. So from this equation, just you calculate the C value. C is equal to this C value you need to calculate. This 2 pi F I am bringing into the numerator. So here C value we need to calculate. C is equal to, we will get 2 pi F whole square. This 2 pi F I am bringing here, and this C I am bringing here, and L also will come into the new denominator. C is equal to 1 by 2 pi F whole square into L. So pi equal to 3.14, F is 50, L is 1 Henry. So if you substitute, we will get the capacitance value as around 10 microfarad. Right? Question number 10. Power factor of an inductive circuit can be improved by connecting a capacitor to it in dash. So we can improve the inductive circuit power factor by connecting a capacitor, because capacitor supplies the reactive power. So because of that, power factor is going to improve. So how we have to connect the capacitor with the inductor? We have to connect in series with the inductor. We have to connect the capacitor. In series with the inductor. We have to connect in series with the inductor. Next, question number 11. In series circuit, dash acts as a reference. In series circuit, we will take current as a reference. Question number 12. In parallel circuit, dash acts as a reference. In parallel circuit, voltage will be taken as a reference vector. Next, question number 13. The impedance of a capacitor 3.18 microfarad. So C is equal to, what is the value? 3.18 microfarad is connected to a supply of frequency F is equal to 50 Hz. So we need to calculate the impedance of a capacitor. Impedance of a capacitor is nothing but what? Capacitive reactance. XC value we need to calculate. Impedance of a capacitor is nothing but what? XC. So XC is equal to, what is the formula? 1 by 2 pi Fc. That is equal to 1 by 2 into pi is 3.14, frequency F is 50 Hz, and capacitance is 3.18 microfarad, that is into 10 to the power of -6. Impedance nothing but, it is nothing but what? Ohms. So what is the value we are going to get is around 1000, approximately we will get the 1000 ohm impedance. Next, question number 14. The product of voltage and current in a circuit is, so V into I is called what? So V into I is called operant power. So we call this as a operant power. Units of operant power is volt ampere or kilovolt ampere. We have three types of power: active power, reactive power, operant power. Question number 15. A capacitance of C farad is connected across a capacitance is how much? C farad is connected across a 50 Hz sinusoidal voltage source. F is equal to 50 Hz. What is the capacitive reactance? Capacitive reactance value we have to calculate. XC value we have to calculate. What is the XC formula? XC is equal to 1 by 2 pi Fc. So that is equal to 1 by 2 into pi is 3.14 into frequency F is nothing but what? 50 Hz into C. So capacitive reactance nothing but what? Ohms. So around we will get 0.0318 by C ohms. Next, question number 16. The power consumed in AC circuit will be minimum when the phase difference between current and applied voltage is how much? So when the phase difference between current and applied voltage is 90 degrees, then we'll have the minimum power consumption. So what is the power consumption formula? VRMS IRMS cos pi. So when pi becomes 90, cos pi becomes what? 0. Then power consumption becomes almost 0 or minimum. So when the phase difference between voltage and current is 90 degrees, then we will have the minimum power consumption. Question number 17. In RL circuit, dash the voltage. In RL circuit, current lags behind the voltage. In RL series circuit, current lags behind the voltage. Current magnification occurs in dash. Current magnification occurs in RLC parallel circuit. In RLC parallel circuit, current magnification is going to occur. At resonance, and in L and C, that current magnification is going to occur. Next, 19th question. Resonant frequency FR of a series RLC circuit is related with the half power frequencies F1 and F2. Lower cutoff frequency, upper cutoff frequency, and resonant frequency. What is the relation? FR is equal to root of F1 into F2. The relation between resonant frequency and half power frequency F1 and F2 is FR is equal to root of F1 and F2. Next, question number 20. Ratio of voltage across inductor. Voltage across inductor is VL to the applied voltage VL by V. At resonance, it is defined as Q factor. Q factor nothing but what? VL divided by V. In series RLC circuit, magnitude of the resonant frequency can be changed by changing the value of. So what is the resonant frequency formula in series RLC circuit? FR is equal to 1 by 2 pi root LC. by changing the L value or by changing the C value, we can change the resonant frequency. So by changing L or C values. Next, question number 22. In an RLC parallel circuit, the power factor at resonance. The power factor's resonance is unity. Cos pi value is 1. Next, question number 23. Q factor of a resonant circuit is defined as. So what is a Q factor? Q factor of a resonant circuit is equal to 2 pi into maximum energy stored. 2 pi into maximum energy stored divided by energy dissipated per cycle. Energy dissipated per cycle. 2 pi into maximum energy stored divided by energy dissipated per cycle. This is a definition of Q factor in the resonant circuit. Next, question number 24. A RL series circuit, the magnitude of the impedance is given by. So magnitude of the impedance in RL series circuit is root of R square plus XL square. XL nothing but inductive reactance. XL is equal to, what is the formula? XL is equal to 2 pi FL. Under resonance condition, dash and F is equal to dash. So under resonance condition, inductive reactance XL and XC both are equal. XL and XC are equal, and resonant frequency F is equal to, what is the formula? 1 by 2 pi root LC. Next, quality factor Q0 is equal to, in terms of R and C value we need to find. Quality factor Q value we need to find in terms of C and R. So quality factor Q is equal to omega naught CR or omega naught RC. So these are the bits, fill in the blanks questions from RL, RC, RLC parallel circuit. Thank you. In the next lecture, we'll start with the 3-phase circuits, multiple choice questions and fill in the blanks. Thank you.